Hi, I'm Amir Hossein Mirza Bozorg, and in this video I'm gonna talk about Comprehensive Abaqus Package Chapter 13, Writing Codes in Abaqus Part 1. How to ask your video-related questions. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We will try to answer all questions regarding the video details in the comments below. New Abaqus users who want to develop their modeling skills faster in their projects can request user-oriented online and offline services. Subsequently, we offer step-by-step guidance, tutoring, and consultancy regarding their problems. The online service includes online sessions, and the offline service includes creating special tutorials. In addition, a combination of the two can be requested. This is the table of content for part 1 of chapter 13. Now I want to start chapter 13. It's about writing codes in Abaqus. We have three kinds of writing codes in Abaqus. The first one is writing subroutines. Subroutines must be written in the Fortran language. We can introduce a new function, mathematical relation, or behavior to the Abaqus solvers by using subroutines. Before running the model with subroutines, the appropriate Fortran compiler and Visual Studio versions must be linked with Abaqus. In the Fortran language, we call the function as the functions as subroutines. So subroutines are a kind of functions, and by using these functions, you introduce a new thing to Abaqus. For example, a new material, a new mechanical behavior, a new element type, a new plasticity behavior or plastic formulation, or something like that. The other one is writing scripts and macros. Scripts and macros must be written in Python language. We can control the CAE environment and model by writing scripts and macros instead of using the CAE tools directly. In this session, until now, I have used CAE tools to create the models, but you can also write code to define these models. Because every CAE tool or every command in the CAE environment has something identical or equivalent as a Python code. Okay, as a Python code. This will increase the speed of modeling significantly and can be used when you must create many models which are different in a few characteristics. For example, let me save and close. For example, we have a plate. There is a hole on it, and we fix one side and we apply force on the other side. Okay, very simple. I want to see that by changing the radius of the hole, how much the stress concentration factor changes here. Okay, we know that the profile of stress will be like this. Okay, this is, for example, sigma max, and this is sigma 0. I want to find the sigma max to sigma 0 when the radius changes. So I must create, for example, 10 models, and in each one I must change the radius and then run the model and find the sigma max and divide it by sigma 0. I can do it via a Python script, which must be ran for several times, okay, to create each model and run it and find its sigma max. That's it. We can do it by using Python scripting and writing a script. The other one is writing keywords. Some of the capabilities and commands in Abaqus do not have a CAE usage, and we must add or modify keywords of the model to use them. The language of keywords belongs to Abaqus itself and is not used anywhere else. In the chapter 10, if you remember, I defined, I wrote the mode shapes, the buckling mode shapes on a fill file, and then I used them to define imperfection. For both the procedures, I wrote keywords, because they didn't have a command in the CAE environment in my Abaqus version. Even until version 2022, they don't have any CAE usage, okay? Defining imperfection and also writing the eigenmodes on the fill file. And we wrote keywords. Like this is the example for writing keywords, and also its language is it's only limited to Abaqus itself. It is not actually a language, okay? They are a combination of commands, not language like Fortran or Python. Notice that each of these writing methods has its applications, and they cannot be used instead of each other. They are like different army forces, like Air Force, Navy, and Ground Force. Each of them has their capabilities and tasks and can operate independently from the other troops. Also, they can do combined operations. Okay, in the army, for example, Navy and Air Force, they can do combined operations, or Air Force and ground forces, or even Air Force individually. Also in Abaqus, it's the same. For example, in a project, you can use Python script and subroutines, or Python script and keywords, and anything like that. But there is no subroutine that can do or can work like keywords or Python scripts. Okay, they are completely different. Now I want to talk about subroutines. Subroutines in Abaqus. In the Fortran language, we call the functions as subroutines. They are two types of subroutines in Abaqus: user subroutines and embedded subroutines. What we are talking about in this chapter is only about user subroutines, which we write them. Embedded subroutines were discussed in chapter 12. If you remember, I talked about Abaqus documentation and I talked about embedded subroutines, that they are not included in the documentation. Okay? So the documentation is not complete. The Abaqus documentation is not complete, unfortunately. Each of the Abaqus solvers has its subroutines. Each subroutine has its interface, and for writing a subroutine, you must copy the interface in a new Fortran file with .f or .4 format and then modify it according to your own. I will do this in chapter 14 when I want to define heat flux, moving heat flux due to the laser, and I want to do lap joint weld, okay, by using laser. And when I want to define moving heat flux, I will write deflux subroutine. Some of the Abaqus standard subroutines and Abaqus explicit. Some of the I must edit it. Some of the Abaqus standard and Abaqus explicit subroutines have similar names, logic, and application, like UMAT and VUMAT, deload and VDeload. You can see that only V is different between their names, and both of them they have similar usage, and even they have similar interface. And everyone who can write UMAT, after some exercises and after some time, he or she can also write VUMAT, and also in the reverse direction. Examples of user subroutines. For example, defining distributed surface and volumetric loads. We must use deload and vdeload subroutines. For example, we have a truck, okay? We have a truck. For example, this is a truck, okay? It has 6 wheels. Okay, and it is moving on the ground. If you look at it from the top view, what you see? This is the road, okay? It has a speed. This is the road, and these are the effect of wheels They are the effect of wheels on the ground. Okay? And all of them move with the speed of v. Okay? Suppose that we must simulate this problem and we want to calculate the stress induced on the ground. So we must model the wheels, or we must only define these areas, but they are moving. Okay, they are moving distributed loads. We must define pressure, but this pressure is moving, so we must write code. They are moving loads. They are moving loads. We have several kinds of moving loads in the physics, and in the next course, in the Abaqus course for industry, I will explain all of them, and I will give you a general definition for moving loads from the mathematical point of view, and then I will introduce you several ways to define them in Abaqus, and also I will solve examples for each of the procedures. And but I told you I will do this in the Abaqus course for industry. And also defining arbitrary boundary conditions. We can for defining some complex boundary conditions, we must use subroutines, and for example disp or v-disp subroutine. Or defining new mechanical behavior. For defining new mechanical behavior, we have a lot of options in Abaqus. One of them, which is the most complex one, is using UMAT or VUMAT subroutines. Sorry, I must also edit this part. You can write every, I wanted to say you can write or introduce every constitutive law, every physical constitutive law, and introduce it to Abaqus. I must modify this box. The other one is U-hard or VU-hard subroutines. They can be used for defining new plastic behavior. And this procedure is much simpler than using UMAT or VUMAT. The other one is using USDFLD or VUSDFLD subroutines. They can be used to modify the material models available in the property module to define new behaviors. And also it is much simpler than UMAT and VUMAT. For example, as you know, we use Johnson-Cook plasticity. Okay, we use Johnson-Cook plasticity in the examples of chapter 11. We can change its definition using USDFLD subroutine. For example, we can make the plasticity definition dependent to an independent variable in the simulation, okay, and other things. Also, I have good experience using USDFLD and VUSDFLD subroutines, also for using U-hard and VU-hard subroutines. And when you write a subroutine, then you must run the model with subroutine, and you must attach the subroutine to the job from the general tab of the edit job box. Here you must select your subroutine. here I have written that for a simulation, only one Fortran file can be attached to the job. If you want to use several subroutines, you must write all of them in a Fortran file, one after another. These subroutines can be dependent on each other or independent from each other. For example, we use the VUMAT subroutine for the material definition and the VDLOAD subroutine for the load definition. They are independent of each other. Or we use both the USDFLD and UHART subroutines for material definition. They can be dependent or they can be dependent on each other. For example, here I open this subroutine file. This is deflux subroutine for defining moving heat source or moving heat flux. And this is the USDFLD subroutine to define field variable and a state variable to visualize the melted regions in the lap joint weld. And these subroutines are completely independent, okay? But in this case, we have two subroutines. The first one is the USDFLD to define the independent parameter which controls the simulation. And then we have the UXPAN subroutine that uses this independent parameter, and then some calculations will be done. So here UXPAN subroutine is dependent on the USDFLD subroutine. And as you can see, they are written after each other. Oh, also here it doesn't have any title. I will edit all of them and then send the modified slides to you. Writing scripts and macros. Now I want to talk about writing scripts and macros. About the scripts, you can write for loops or while loops in your script to define several models. A model will be created, submitted or not, and then the next one will be done. You can do parametric modeling or optimization using scripts. I told you, for example, we change the radius of the hole every time and rerun the model. And about the macros. Macros are similar to scripts, but they are simpler. You can use them to automatically add something to your model, like defining several steps or interactions. Or writing and using macros will save you time significantly. For example, in a simulation, you must create 100 steps which are similar to each other. And they are similar to each other, so if you want to do it from CAE, you must define 100 steps one after another, and it is very time consuming and it's cumbersome. But you can do this via writing macros. And about writing keywords, yes, it was about writing scripts and macros. For example, here we have a script for defining a model. I will run it at the end of this chapter, okay? Also, it has one for loop, you can see, one for loop to define several models, and in each model the position of the hole is changed. There is a hole on a beam. Okay, it is changed. And I will also run it at the end of this chapter. Yes, about writing keywords, we have two procedures. First, writing keywords in the IMP file, or writing keywords from Abaqus CAE. In chapter 10, I wrote keywords in Abaqus CAE, okay, not in the IMP file. Writing keywords in the IMP file. If you modify your initial CAE model, you must write input file again. If you modify your initial CAE model, you must write input files again and add keywords to it. Because by writing the IMP file, the keywords will not be because by writing the IMP file again, the keywords will not be added to it. I will explain this paragraph again when I am solving an example for you. First of all, you must create the CAE file, and then you click on write input, and then the input file is created. Then you must modify the input file and then create a job from the IMP file and then run that job. So when you change the CAE model, the original CAE model, then the IMP file is not changed automatically. Again, you must write input and again do the modifications and then create a new job from the new IMP file and then run it. Okay? So it takes time. But if you write keywords from the CAE, like what I did in chapter 10, then there is no problem. When the model is complete, you must create a job from the model and click on write input to create the IMP file. Then you must open it and add keywords in the correct locations in the IMP file. Then you must create a job from the IMP file and run it. This is your main job. You must not import the modified IMP file into the Abaqus CAE again, because most of the time it will not be imported correctly. I told you this point in chapter 12 when I told you that in the documentation we have IMP files, and if you want to run the IMP file, please do not import it into the Abaqus CAE and then create a job. Please create a job directly from the IMP file. Okay? I told you this because it is not imported correctly most of the time. And about writing keywords from Abaqus CAE, only some of the keywords can be added from Abaqus CAE. All of the keywords can be added into the IMP file, but not all of them can be added to the Abaqus CAE. Like chapter 10. If you add a keyword from the Abaqus CAE, there is no need to write them again when you change the CAE model, because the keywords will be automatically added to the new IMP file. Okay? This is its advantage. For example, keywords needed to incorporate buckling modes to define geometric imperfections for post-buckling analysis. There is no need to modify the IMP file again after modifying the CAE file, because when you modify the CAE file and write input, all of the keywords are added automatically to the new IMP file. Using 2 or 3 writing code procedures simultaneously. you must use 2 or 3 writing code procedures in some complicated projects simultaneously. For example, example 1. Post-buckling analysis of a column created from a particular material that must be introduced via the VUMAT subroutine to the abacus. So you must add keywords of imperfection definition to the keywords, and then also you must attach VUMAT subroutine to your job. About example 2, some of the subroutines cannot be called from the Abaqus CAE, and they do not have CAE usage like the SIGINI subroutine. User subroutine, SIGINI subroutine is used to define an initial stress field. So the IMP file must be modified for calling them. Let me show you. Okay. I go to the documentation. I search SIGINI. Defining initial stress. Defining initial stresses in user subroutine SIGINI. For complicated cases such as elbow elements in Abaqus standard, the initial stress field can be defined by user subroutine SIGINI. In this case, Abaqus standard will make a call to subroutine SIGINI at the start of the analysis for each material calculation point in the model. You can then define all active stress components at each point as functions of coordinates, element number, etc. Here you can see that input file usage is this. Abaqus CAE usage. User subroutine SIGINI is not supported in Abaqus CAE. So if you want to use SIGINI subroutine, you must edit the IMP file. And here we have that keyword initial condition type stress. But here you can see that they have written initial conditions type stress user. So at the end of this command line, I must add user. And here I have added it. User. So here I must attach a subroutine file for SIGINI subroutine to the job of this IMP file and run it. Here I have written user myself. And how much time we have? Okay. Now I want to talk about infinite elements as an example for writing keywords in Abaqus. How to purchase packages or individual chapters. Each of the packages and individual chapters includes CAE, JNL, and IMP files, step-by-step tutorials with detailed explanations and investigation of the results, slides and reference papers and standards. Packages, specifications, and payment details are provided in the video description. Also, you can pay the cost of the packages in 2, 3, or 4 installments according to your budget or income. In the future, updates will be provided for free for everybody who purchases each chapter or each package. The cost of each chapter or package will increase after each update for new buyers, but those who purchase the package would have endless access to all the upcoming updates. This will make the content up to date for new needs and new problems which must be solved via FE simulation. You can contact us using Telegram or WhatsApp, or you can send email to us. We can have one-on-one tutoring on the AnyDesk WhatsApp, and we can make special tutorials to your order. We can conduct high-quality simulations for your thesis, exercises, and industrial projects. We offer support in writing the modeling and result discussion part of your thesis. We have consulting services for MSc PhD positions or job interviews. And finally, we can help you to prepare the presentation of your simulation works. Now I want to suggest you several related videos of our YouTube channel. Thank you so much for watching this video. Have a good time. Goodbye.